don't have any idea about, but it's a lot. I know that much.
Because don't you have the notion of you have this packet and it diffuses outward,
Yeah,
and the more cycles it makes
Yes.
yeah,
drives the diffusion,
yeah.
and so you have to pull it back. And
Yes.
so that becomes a very important consideration in the stability of
Yeah,
the
what I do know from this slide is that the confinement time that they typically have for a particle is about 1 millisecond. So an ionized particle typically stays in that column without hitting the walls for 1 millisecond. So, and depending upon the velocity, we can calculate how many rounds it makes, but I don't know the number. Okay, so I've tried to model this position data, and the important thing is it's not really important to model the fluctuations, because that is better left to the controller to be robust enough to handle. What you need is an average kind of representation on what the position is, because as you change the vertical field coil or the horizontal field coils, you change any field and the plasma moves either upward or downward, and that is what we don't want. And this doesn't move in the horizontal direction because the way the physics of the machine works, there is no force on the horizontal direction. So the blue line here is an integer order model that I got, and I've not shown the transfer function here, and the green one is one that I got from a fractional order model. What the aim is that we can model this using fractors that Cal showed you in the morning, so we can make a small board out of it, and then it can emulate the whole process, and then we have a controller that controls it. That controller board, the fractional order controller board, is already ready, and after everyone's talk is over, I hope I have enough time to show you how it works with the coupled tank system. So here's how I go about modeling the fractional order system. If G of S represents the integer order system and G hat is the fractional order one, then we're looking to minimize this norm in the frequency domain, and that can be approximated this way. And you just keep varying omega, and over the whole cycle you just search this function and come up with the values that gives you the minimum. So that's how I get my models. And this is the Simulink representation of what I intend to do finally. Is like, if you see this block over here, this is nothing but a fractional integrator, two fractional integrators in parallel. So what is happening over here is this. So I'm just doing that, and that is approximating my transfer function for the tokamak, and the values for which I find out. And there is another block similarly, like YangQuan showed, that is the fractional controller, and in order to test the robustness, I inject some noise, and here are the results. The idea is to keep it at the center, and 0 is the center of the tube, so it rises very quick, and even with big displacement, like for the real system, a 1 millimeter displacement never happens. It's if that big a displacement occurs, that occurs near the end when the plasma will no longer exist. So it's performs pretty well. And just to save time, I have not put in the details or the other plots, but I have put in this one because this represents all the possible combinations. This is like an integer order model with integer order control, integer order model with fractional control. This is fractional model with integer control, and this is fractional model with fractional control. You see that as we go to totally fractional models, the ITAE decreases and the error goes down, and that is good. So here's the basic idea. It's like first get an integer order model for the plasma position.
Very high order.
Yeah, simulate it. Then I make a fractional order model and control it as I showed. In my demo, I will show you how to implement this fractional order controller using only analog hardware. The reason we do only analog hardware is because the time scale, the lifetime of the plasma is 5 milliseconds, Out of that, around only 3 milliseconds is the stable time, and if you have to go through a digital to analog converter and then to a computer and then out again, then there is no way you will be able to control it. So which is why we are focusing on analog control. So I'll show you how this works using Fractors. We have a board ready for this which controls the couple tank system right now. And after that, it's I am going to use the equation that I showed here and use the same Fractor elements to make a board which models the system, and try it first on the fan and plate, which is a delayed system, and a heat flow which shows signs of creep on it, because you never get a steady state, it just keeps on increasing at a slow rate. So those should be two good systems to test analog fractional order hardware on. Once that is done, I can compare all the above emulators and make an actual board which mimics the plasma system, and then hook up two boards to each other, like have a analog hardware fractional plasma model board and a controller board, and see how they fight or control each other.
A board to control another board.
So
It's a really good plan language. Thank you.
So that's this is the board that we have right now. It's a prototype. It looks that way because we made it in a hurry, and
Yeah, we will demo
yeah.
before when we finish everything here. And when we go out, you can take it.
That's what my master's thesis is going to be about, and
So
these are the references.
We already promised if these two boards not fighting each other and not being graduate.